In this tutorial video on industrial instrumentation, we will talk about the second part of flow measurement. The topic of today's discourse deals with variable head or differential flowmeters, under which we have Orifice Plate, Venturi Tube, Flow Nozzle, Dall Tube, Pitot Tube, Annubar Tube, Elbow Tap, Weir and Flume. The Weir and Flume come under open channel flowmeters. In a variable head or differential flowmeter, a restriction in the line of a flowing fluid is introduced by the orifice or Venturi tube or similar devices, and it produces a differential pressure across the restriction element which is proportional to the flow rate. Head flow meters operate on the principle of placing a restriction in the line to cause a differential pressure head. The differential pressure which is caused by this head is measured and then converted to flow measurement. The device is generally termed as obstruction type flow meter. Given below is a picture of a typical variable head flow meter. Here we see how a restriction is inserted in the path of flow, and due to that we see pressure gradients on either side of the obstruction. This pressure gradient is calibrated in terms of flow and flow is measured. In a variable head flow meter or differential flow meter, the proportionality is not linear one but has a square root relationship where flow meter or flow rate is proportional to the square root of the differential pressure. This is derived from Bernoulli's theorem. Velocity head is defined as the vertical distance through which a liquid would fall to attain a given velocity. Pressure head is the vertical distance through which a column of the flowing liquid would rise in an open tube end as a result of the static pressure. Numerically, V equals K under root 2 GH by rho, and Q is given as Ka under root 2 GH by rho, where V is the velocity of the flowing fluid and Q denotes volume flow rate. W is equal to K under root 2 GH by rho, where K equal to A1 A2 by under root A1 square minus A2 square whole into under root 2G. W denotes mass flow rate. The coefficient of discharge is given as CD equal to Q actual by Q ideal. The rate of discharge or the volume flow rate Q is given as A1 V1 in or equal to A2 V2. Applying Bernoulli's equation for ideal flow assumption, we have P1 plus rho V1 square by 2 equal to P2 plus rho V2 square by 2. The differential pressure head del H is given by P1 minus P2 by rho G equal to del H. Q actual is always less than Q ideal, and therefore the coefficient of discharge is always less than 1. And it is because due to losses by friction and eddy motions. Here given are a list of advantages and disadvantages of differential flow meter. The advantages of differential flow meter are they are of relative low cost for large pipelines. They offer widest application coverage for any types of meter. They offer very high accuracy, somewhere between 0.25 and 2%. They can be easily removed without tripping the entire process, and they are highly adaptable. But there are few limitations as well. The limitations are there are relatively higher permanent pressure losses involved in this particular setup. They are difficult for slurryous surfaces. If the fluid contains slurryous particles, they are difficult to manage. They exhibit square root relationship between the head and the flow rate rather than linear characteristics, which limits the usable flow range ability to a mere 3:1 or 5:1 range. Low flow rates are not easily measured, and they face difficulty to measure pulsating flow. Differential flow meters comprise two parts, primary element and secondary element. There is something called vena contracta beta, which ranges between the value of 0.65 and 0.7 is the point of minimum pressure. The point of minimum pressure is located slightly downstream from the restriction at a point where the stream is the narrowest and is called the vena contracta. Beyond this point, the pressure again rises but does not return to the upstream value, resulting in a permanent pressure loss. The primary element causes restriction in the path of flow and produces differential pressure. The primary elements of a differential flow meter can be Orifice Plates, Venturi Tubes, Flow Nozzle, Dall Tube, Pitot Tube, Annubar Tubes, elbow taps, Weir and Flume. The secondary elements measure the differential pressure. It comprises manometers, balometers, force balance and ring meters. An orifice plate is a device used for measuring flow rate, for reducing pressure or for restricting the flow. The orifice meter, when installed in small to moderate sized pipes, is probably the cheapest and the simplest flow measuring device at present, available for metering liquids, gases and vapors. It is not suitable, however, for highly viscous liquids and fluids in a pulsating or extremely turbulent condition. When the fluid flows through the orifice, its velocity increases and the diameter of the jet decreases to minimum at a point v known as the vena contracta. The jet expands until it again occupies the full bore of the pipe. The static pressure profile first shows a gradual decrease over the distance L to M due to frictional losses in the pipe. From M to P, as light rise occurs due to the resistance of the orifice plate, a sharp drop in the pressure occurs from P to R due to the fluid velocity through the orifice. Finally, there is a partial recovery of the pressure from R to S, as can be seen in the figure below. We have this marking M, P, R and S to demonstrate the pressure changes in the orifice plate. The net pressure loss due to friction and turbulence across the orifice is typically about 65% of the pressure difference measured by the DP diaphragm. The fluid flow is proportional to the square root of the pressure difference. Again, we see how pressure tappings are positioned, one in front and one after the restriction. The orifice meters have their own share of pros and cons. The advantages of the orifice meter are they are inexpensive and simple in construction. They offer easy installation with no moving parts. They cater to large range and opening ratios. They have very high suitability and size to price ratio is very moderate. But the limitations are the accuracy is limited in the range of 1% maximum. The range ability is 4:1. Density, pressure, viscosity, all these factors influence the flow measurement. Unrecoverable pressure loss, which is around 65%. Straight and filled in pipelines are required for better results. There are 6 basic orifice meter designs. They are concentric. The concentric ones are commonly used for the general application for any gases, liquids or vapors. The second is the eccentric type, recommended for fluids with extraneous matter to a degree that could clog up the concentric type. The third is the segmental one, recommended for fluids combined with vapor or vapor combined with fluids. The fourth is the square edge, applicable for higher pipe Reynolds number, typically between 5,000 and 10,000. The quadrant ones are for lower pipe Reynolds number, typically somewhere between 250 to 3,300. And lastly, the conical ones for Reynolds number, typically in the range of 25 to 75, that is very low Reynolds number. Here we see the pictures of these 6 principal designs of the orifice plate. The second type of differential flow meter is the Venturi tube or Venturi meter. The Venturi effect is the reduction in fluid pressure that results when a fluid flows through a constricted section of a pipe. Venturi meter is used instead of an orifice plate in process systems where it is important to minimize permanent pressure loss across the restriction device. In Venturi, the restricting element is tapered tube instead of a sharp edge orifice. The tube gives a smoother velocity change which results in a small permanent pressure loss to approximately only 10% of the differential pressure measurement. The tapering edge at the input side ranges somewhere between 19 and 23 degrees, and at the outlet it ranges somewhere between 7 and 15 degrees. We have a center pressure tapping just after the Venturi tube. We have a pressure tapping before the obstruction created by the Venturi tube. The static pressure in the first measuring tube 1 is higher than that of the second, and the fluid speed at 1 is lower than that of 2 because of the cross-sectional area at 1 is greater than that of 2. We already know it from Bernoulli's principle that P1 minus P2 is equal to rho by 2 V2 square minus V1 square. Thus, for Venturi tube, the flow rate actually is given as CD A2 ME under root 2G by W P1 minus P2, where V1 and V2, P1 and P2 are the average velocities and pressures at the inlet and throat respectively. CD is the discharge coefficient, A2 is the cross-sectional area of inlet, W is the fluid specific weight, E is the temperature constant factor, rho being the density, and M is given as 1 by under root 1 minus A2 by A1 whole square. Like any other devices, Venturi tubes have their own advantages and disadvantages. The advantages are they offer less significant pressure drop across restrictions. They also offer less unrecoverable pressure loss, and upstream and downstream straightness of pipe requirement is very low. The disadvantages are they are expensive than orifice, they are bulkier in construction than orifice. A pair of Venturi tubes on a light aircraft are shown in the two pictures below. Here we hold a comparison between an orifice plate and a Venturi tube. When we talk about the reducing element, the orifice has sharp edges and the Venturi has tapered ones. The permanent pressure loss for a orifice plate is 65% and for Venturi is only 10%. The Reynolds number, orifice plates are very less sensitive to them, but the Venturi tubes are highly sensitive to Reynolds number. Orifice plates greatly get affected by dust and dirt. For Venturi tubes, dust and dirt have marginal effects. Orifice plates are cheaper than that of the Venturi ones. Accuracy of orifice is lesser than that of Venturi. Orifice is easier to install than the Venturi ones. A flow nozzle is a flow tube consisting of a smooth convergent section leading to a cylindrical throat area. Flow nozzle is a restriction consisting of an elliptical contoured inlet and a cylindrical throat section, as shown in the figure. Pressure tabs are used to measure the differences in the static pressure created by the flow nozzle and are commonly located 1 pipe diameter upstream and half pipe diameter downstream from the inlet face of the nozzle. The flow nozzle is similar to the Venturi but are in the shape of an ellipse. They have a higher flow capacity than orifice plates. Another main difference between the flow nozzle and the Venturi is that although they have similar inlet nozzles, the flow nozzle has no exit section. These devices are more cost effective but As such, they provide less accuracy than Venturis and have a higher unrecoverable pressure loss. Flow nozzles can handle larger solids and can be used for higher velocities, greater turbulence, and high temperature applications. They are often used with fluid or steam applications containing some suspended solids and in applications where the product is being discharged from service. Numerically, the flow rate is given as Q actual equal to K E A naught under root 2 G by W P1 minus P2, where K equal to CD by under root 1 minus A2 by A1 whole square, or CD by under root 1 minus D2 by D1 whole square. The symbols have their usual connotations. Flow nozzles find application to measure flow rates of the liquid discharged into atmosphere. They are used in measurement where suspended solids have the property of settling, high pressure and temperature flow streams, high velocity and high turbulence applications. The advantages of flow nozzles are cheap and easy installation, compact size, and high discharge coefficient, while the disadvantages are low lost pressure recovery and high maintenance. The Dall tube is a combination of Venturi and Orifice. It has shorter tapering intake like a Venturi with a low yet sharp pressure profile like an Orifice. It is used in high flow rate applications. Dall tube consists of two conical reducers inserted into the fluid carrying pipe. It has a shape very similar to that of Venturi with a throat. The construction of Dall is much simpler than that of a Venturi, which needs complex machinery. It is much shorter in length, which makes its insertion into the flow line much easier. Its perimeter pressure loss is only 5%, where for that of a Venturi it is about 10%. On the basis of maintenance and operational life, Dall and Venturi both are same. The flow rate in a Dall tube is given by the formula V equal to K under root dP, where V is the volumetric flow rate, dP is the differential pressure, and K is the constant derived from the mathematical parameters of the primary elements. Dall tubes find application in gas transmission, in clean gases, in hydrocarbon fluids, and in flow in closed circular pipes. Higher ratio of pressure developed to pressure loss. Compact and suitable high flow application compared to Venturi, the overall energy loss is half, permanent pressure drop and loss is negligible, short size and easy installation, highly accurate for clean fluids, low maintenance and low wear and tear and erosion. All these are the advantages of a Dall tube. The disadvantages are complex manufacturing process and highly turbulent sensitive. A basic pitot tube consists of a tube pointing directly into the fluid flow. As the tube contains fluids, the pressure can be measured. The moving fluid is brought to rest stagnation point as there is no outlet to allow the flow to continue. This pressure is the stagnation pressure of the fluid, which is also known as the total pressure or the pitot pressure in aviation. The pitot tube is a tube with one open end facing the incoming fluid stream. The pitot tube measures flow based on differential pressure and is primarily used with gas fluids. The measurement of the total pressure, that is dynamic plus static, is done, and a second measurement is required for the static pressure. The difference between the two measurements give a value for the dynamic pressure. The flow rate, like any other devices, is calculated from the square root of the pressure. In calculating the flow rate from the pressure, the calculation is dependent on factors like tube design and location of the static tip. The pitot static probe incorporates the static holes in the tube system to eliminate this parameter. The Pitot tube is also used to determine the velocity profile in pipe, and this is done by measuring points at various distances from the pipe wall to construct a velocity profile. The Pitot tube is a primary device and it has the advantage over orifice of practically no pressure drop. Its usefulness is limited to clean gases and liquids only, as the sensing element is very small orifice. Foreign materials tend to clog the opening in the tube, and the classical Pitot tube senses impact pressure at one point only, thus decreasing the accuracy. If we assume a steady, one-dimensional, uncompressed, frictionless fluid with no heat loss from free stream velocity and apply Bernoulli's principle between a point in the free stream and another point at the tip of the stagnation tube, we get P static by rho plus V square by 2 equal to P stagnation by rho. From there we get V equal to under root 2 into P stagnation minus P static by rho. Pitot tubes develop a very low differential pressure which is often difficult to measure with the secondary element. Also, the accuracy of these Pitot tubes is dependent on the velocity profile of the fluid. The velocity profile is again affected by turbulence in the flow stream. If we apply Bernoulli's theorem, we get P by W equal to V square by 2G plus P0 by W, where P is the pressure at inlet and P0 is the static pressure. Thus, the velocity profile is obtained by V equal to under root 2G by W P minus P0 equal to under root 2G by rho P minus P0. Thus, the mean velocity measured by a Pitot tube is given as Cv under root 2G by W into P minus P0 or Cv into under root 2G by rho P minus P0, where Cv is the velocity correction factor. In a Pitot tube, the stagnation pressure is given as static pressure plus dynamic pressure. Thus, P stagnation equal to P static plus rho V square by 2. Thus, the flow velocity V is given as under root 2 P stagnation minus P static by rho. Here we see a Pitot tube mounted on an airbus. Pitot tubes find application in determination of airspeed in aircrafts, water speed of a boat, air and gas flow velocities in certain industrial applications. The advantages are low to no resistance to flow and very inexpensive. However, the disadvantages are wet steam occasionally blocks bottom holes, therefore requires horizontal installation. Special care is needed in installation orientation. They are highly turbulence sensitive and limited turn down of 4:1 due to square root relationship between the pressure and the velocity profiles. A Annubar tube is also known as an averaging pitot with multiple pressure tapping to draw the average flow rate. A pressure difference is created in the flow path which is proportional to the fluid velocity squared. It works based on Bernoulli's principle and flow rate Q is proportional to K under root dP. An Annubar is very similar to that of a Pitot tube. The difference is that there is more than one hole into the pressure measuring chamber. The pressure in the high pressure chamber represents an average of the velocity across the pipe. Annubars are more accurate than Pitot tubes and they are not as position sensitive to the velocity or the velocity profile of the fluid. The Annubar can be used for both volumetric flow rate and mass flow rate. To measure volumetric flow rate for liquids, the flow rate is given as QV equal to NK d square FAA into under root dP by GF. For gases, the volumetric flow rate is given as Nk d square Fa under root dP by rho F, and the mass flow rate for both gases and steam is given as Nk d square Ya Fa under root P into dP by T, where dP is the differential pressure, K is the Annubar flow coefficient, D is the inner pipe diameter, P is the static pressure, T the flow temperature, N is the conversion factor, and GF is the specific gravity factor. Advantages that Anova offers are: they are operational even through small openings. The velocity sample can be taken at multiple points. Minimal obstruction and low pressure drop, low permanent pressure loss, and simple inexpensive construction and installation. However, the disadvantages are fragile construction, low differential pressure, and limited to single point measurement. An elbow tap meter operates on the principle that when liquid travels in a circular path, centrifugal force is exerted along the outer edge. Thus, when liquid flows through a pipe elbow, the force on the elbow's interior surface is proportional to the density of the liquid times the square of its velocity. In addition, the force is inversely proportional to the elbow's radius. Elbow tap flowmeter operates on the principle that when a fluid moves around a curved path, the acceleration of the fluid creates centrifugal force. In operation, the centrifugal force results in a higher pressure on the outside of the elbow than on the inside. Thus, a differential pressure is produced which is proportional to the square of the flow through the elbow. A pipe elbow can be used as a primary device. Elbow taps have an advantage, that is, most piping systems have elbows that can be used. In applications where cost is a factor and additional pressure loss from an orifice plate is not permitted, the elbow meter is a viable differential pressure device. If an existing elbow is used, then no additional pressure drop occurs and the expense involved is minimal. They can be used or they can be produced in situ from an existing bend and are typically formed by two tapping drilled at an angle of 45 degrees from the bend. These tappings provide the high and the low pressure tapping points respectively. Tapping at 22.5 degree has shown to provide more stable and reliable readings and are less affected by upstream piping. However, 45-degree tappings are more suited for bidirectional flow measurement. Velocity, pressure and elevation above the datum level for the pressure taps on the inside and outside surface of a 90-degree elbow can be related like Ck V square by 2g equal to P0 by rho g plus Z0 minus Pi by rho g minus Zi, where Zi and Z0 are the lowest and the highest points of tapping respectively. The flow rate is measured by the following equation: Q equal to A into V, which gives us A by under root Ck into under root 2g P0 by rho g plus Z0 minus Pi by rho g minus Zi, which gives us C dot A into 2g by P0 by rho g plus Z0 minus Pi by rho g minus Zi. Elbow taps are simplified in installation and very inexpensive, but they offer very low accuracy. Next up are the open channel methods. The open channel refers to any conduit in which liquids flow with a free surface. Included are tunnels, non-pressurized sewers, partially filled pipes, canals, streams and rivers. Of the many techniques available for monitoring open channel flows, depth-related methods are the most common. These techniques presume that the instantaneous flow rate may be determined from a measurement of the water depth or head. The two oldest and most popular open channel metering techniques are the Weir and the Flume. Weir is the first type of open channel flow meter, which is a simple dam in a channel obstructing the passage of flow. There are three constructional types. They are rectangular, cupoidal or trapezoidal, and V-notch. The flow rate over a weir is a function of the weir geometry and of the weir head. The weir head is defined as the vertical distance between the weir crest and the liquid surface in the undisturbed region of the upstream flow. Weirs are variable head, variable area flow meters employed for measuring large volumes of liquids in open channels. The device operates on the principle that if a restriction of specified shape and form is introduced in a flow path, a rise in the upstream liquid occurs, which is a function of the flow rate through the restriction. Weirs operate on the principle that an obstruction in a channel will cause water to back up, creating a high level behind the barrier. The head is a function of flow velocity, and therefore the flow rate through the device can be measured. Weirs consist of vertical plates with sharp crest. The top of the plate can be straight or notched, and based on that they are either rectangular or trapezoidal or V-notch. Applying Bernoulli's equation at undisturbed region of upstream flow and at the crest of the weir, we get h plus v1 square by 2g equal to h minus y plus v2 square by 2g. v1 and v2 are the upstream flow and flow at the crest respectively. v2 is given as under root 2g h plus v1 square by 2g as derived from the previous equation. If v1 is small compared to v2, then velocity of layer of fluid is simply under root 2gy, where y is equal to the depth from the top surface of the water level. For a weir, the general elementary discharge is given as under root 2gy Lw by dy. Elementary discharge of thin layer Q is given as CD under root 2gy Lw dy, where CD is the coefficient of discharge varying between 0.57 and 0.64 and Lw is the actual crest height. The weir flow rate Q actual is given as Qw equal to CD Lw under root 2gy integration 0 to h under root y dy, which boils down to 2 by 3 CD Lw under root 2g h raised to 3 by 2. For a rectangular weir Q, the flow rate is given as 2 by 3 CD Lw minus 0.2 h into under root 2g h raised to 3 by 2, which equals to 3.33 L minus 0.2 h into h raised to 1.5. For cupoidal or trapezoidal weir, the flow rate Q is given as 2 by 3 CDL under root 2GH raised to 2.5 plus 8 by 15 CD under root 2G H raised to 2.5 tan theta by 2, which is equal to 3.367 into L into H raised to 2.5 upon simplification. For V notch weir, Q is given as 8 by 15 tan theta by 2 under root 2g h raised to 5 by 2, simplified 2.48 tan theta by 2 h raised to 2.5, where Q is the volumetric flow rate in cubic feet per second, L is the width of the crest, theta is the V notch angle, and h is the head in feet. The second type of open channel flow method is the flume. Flume generates upstream liquid level height that changes due to change of the flow rate. The most common flume design is the parcel flume, The parcel flume is a fixed hydraulic structure as shown in the figure. We see the top and the side view of the parcel flume. Flumes are generally used when head loss must be kept to a minimum or if the flowing liquid contains large amounts of suspended solids. Flumes are to open channel what Venturi tubes are to closed pipes. Popular flumes are the Purcell and the Palmer Bowler's design, but the most famous one is the Purcell one. The Purcell flume consists of a converging upstream section, a throat, and a diverging downstream section, as can be viewed from the picture here. Flume walls are vertical and the floor of the throat is inclined downward. Head loss through Purcell flumes is lower than for any other type of open channel flowmeter. High flow velocities help make the flume self-cleaning. Flow can be measured accurately under a wide range of conditions. For the Palmer Bowler's flume, it has a trapezoidal throat of uniform cross-section and a length about equal to the diameter of the pipe in which it is installed. It is comparable to a Purcell's flume in accuracy and in ability to pass debris without cleaning. A principal advantage is the comparative ease with which it can be installed in existing circular conduits because a rectangular approach section is not required. Discharge through wires and flumes is a function of level, so level measurement techniques must be used with the equipment to determine flow rates. Staff gauges and float operated units are the simplest devices used for this purpose. Various electronic sensing, totalizing and recording systems are also available in Flume, open channel flow measurement. The free flow discharge in a flume is given as Q actual equal to Ca2 by under root 1 plus A2 by A1 whole square plus under root 2 GH. Simplified Q actual equal to C HA raised to N minus QE, where QE is the submergence correction factor, C is the free flow coefficient valuing between 0.85 and 1, and HA is the head at primary point, and N varies with the flume structure. Despite many several advantages, flume has certain drawbacks. The drawbacks are it requires a drop in elevation. The local flora and fauna gets affected by flume design. Upstream bypass and downstream scour may occur, and empirical, so not very accurate measurements are obtained. For further reading on variable pressure head and differential flow meter, one can refer to the following links and chapters. Thank you.